We're going to kind of camp on scale factors, but converting and all of that is not going anywhere. So you get these two diagrams. We're assuming they're similar. Similar doesn't just mean they kind of look alike. Similar means that every dimension has been affected by the same scale factor. It has been increased or decreased by the same amount. Every single side of this, of the original, this is our original, right? To create this new shape, the same, it has been increased by the same amount everywhere, okay? So we are asked to find, really just at face value here, we're asked to solve for this side here, and we're asked to solve for this side here, right? But what is the first thing you need before you even go and solve for the missing sides? The first thing you should figure out. Most, you have a, no? What's the first thing you need to even start solving for anything? Scale. You can actually just find a scale if you want, because it's not asking you to find a scale factor. Or you go ahead and find a scale factor. It's up to you how you want to do this, right? So I'm not asking you specifically to find a scale factor. So I'm just going to turn off the front lights here. Yeah, so what is important really is if I use the word original, then this is what we would refer to as the new shape. Okay, so let's imagine if we're asked to find a scale factor, right? Find the scale or scale factor. Right? You gotta find, it's basically what relates these two shapes. Right? What relates these two shapes? So I'm gonna go ahead and do that. So K, how about we go scale first? Sorry, I jumped that step. But you obviously would want new compared to original, correct? I would have given this to you. So we need to relate two sides, right? So we're going to relate this side here to that side there. They correspond, right? And the reason I'm picking those two in particular is because I know both of them, right? I know the dimension of both. So the new would get the 5 yards, and the original would get the 4 inches. You would have to just by visual examination, you'd have to agree that the original has been enlarged, right, to get that new shape. So watch out for that. This would be the scale. Okay, this is your scale. Different units are okay. No decimal, so we don't have to multiply anything. So let's find our scale factor. To find a scale factor, we would go, right, new over original, like that. And so we can go 5 yards over 14 inches, like that. And we need to convert our units here. So 5 yards, I know that 1 yard, did I give you the yards and inches, right? 36 inches. Pretty sure I gave this to you. 36 inches. Cancel, cancel. Just to keep practicing our conversion skills, right? So 5 times 36, it's 180 inches. Which means that I can now rewrite the 5 yards into just 180 inches over 14 inches, which allows me to conveniently cancel out the units, which is perfect. The 180 here came in there, right? And at that point, you can this can be written as, let's put this in a cloud. Everything goes on the cloud these days, right? So K is really 180 over 14. I showed you the trick to simplify fractions, right? On the calculator if you'd like. But you can also just go 180 divided by 14, and it's not quite a whole number. So I just leave it like that as a fraction. And then divided would be 12.86 as a percent, right? This would be 1,285.71%. If you wanted to state it in all three formats, that's how you would do it. So this is basically, this is a very important step, right? That would be step number 1. But notice that I did say or scale factor, because it didn't ask specifically for you to figure that out. Okay. This is the scale factor. And we like the scale factor because it's without units, right? And so we can just apply it to anything. We don't have to worry about the units there. I'm just going to show you the trick, right? 180, it might come in handy next year. So you would just type that in and then go math 1 and hit enter, and it reduces it to 90 over 7, right? So that's as reduced as you can get it. But I'm not going to stress over that in this unit, okay? In fact, we don't reduce fractions, really. We don't care about that all that much. We will do like slope-intercept form. Remember that, IPR, the equation? We don't simplify because we have kind of ugly equations that you will get. We just type it into our calculator, we graph them, and we find points and stuff like that. No problem. Doesn't affect one bit. Okay, so now we need to continue our journey. So if you want to find x, here's my other highlighter. I'm going to kind of focus on that. Hey, this side corresponds to that side. This side corresponds to that side. I have a blank here, but no problem. I already have a scale. Right? So here you have to watch out. I'm going to use the scale to help me out here. Why is that? Because I have yards and I have inches, right? Yards and inches. And so it's okay to keep yards and inches separately. So 5 yards over 14 inches would be equal to 3.5 yards, right? 3.5 yards over x. And so x is just 3.5 times 14 divided by 5. It's a bit of a shortcut, right, from what some of you are used to, but that's okay. I think we all have seen cross multiplying and dividing quite often. And what's my answer going to be, guys? If you have yards and yards, then your answer will, if this is inches, this would also be in inches, right? So 3.5 times 14 divided by 5. That's 9.8 inches, right? I'm going to circle that. That's my answer for x. I'm going to block that off. I'm going to do the same thing again. So if you have a different highlighter, I'm running out of highlighters here. Orange. Let's do orange. This one goes with that one. No problem. I proceed the exact same way. 5 yards over 14 inches. In this case, you got to watch out, right? It's the 11 inches, right? That is known, so I put that here, 11 inches. And this is going to be, let's call this y, right? And that's going to be in yards. So that's 11. I will actually use the units here so you can see how they cancel out. Right, 11 inches times 5 yards divided by 14 inches. I apologize if this is a bit small, guys. I know it's a bit crammed. I should have left a bit more space. But here the inches cancel out right here. So you're left with yard, just to confirm that we're doing things right. So it'll be 55 divided by 14. That's 3.993 it is actually yards. We can actually write that in, right? I'm just going to write these in here. 3.93 yards. And this one is 9.8 inches. Note to myself, leave more room next time. All right, so that's how that works. Let's say you would have used your scale factor, this one here. You would have gone 180 over 14, right? And then this would have been 3.5 yards. Careful. Your answer would have been in yards, because remember the scale factor has no unit, so this would have been unitless. So whatever unit you start with, that's the one you end with. So then maybe some converting is needed if you want to answer in inches at the end. So because of the different units and the different shapes, I just stuck with a scale. I used that scale here. But remember, everything is connected. It should all jive regardless of how you proceed. Okay. C. Can I ask you to try that one to warm up a bit? Just try to solve for C. Remember, scale factor is where it's at. What we've been doing is where it's at. So try to do that one on your own. Couple minutes. Remember the attempting part. It's important that you attempt it. So this is the key right here. Scale factor is given. You don't have to find it. It's right there. Right? So this is K, which is 62%, which is also 62 over 100. I like to keep it as a fraction if at all possible. So that's what I'm going to use. You have a can of pop, right? Pop can, and you know that this one has 12 centimeters, right? That's the height of this one. We will call this original. That's the one you start with. A similar can has been made using a scale factor of 62%. So what's the similar one? Is it bigger or smaller than the original? It's smaller, less than 100%. So, right, like I want you to see everything is connected. You can check your work, right? So we're asking, hey, what's the height of this? And we call this new. If this is the original and this is the new one. Right? So how are they related? Scale factor is the key, right? So we'll say 62 over 100. Right? This. Let me backtrack here. Sorry for all the erasing, but I'm always using this formula, right? I gave you this earlier. Scale factor is new over original, right? Use this formula, it's there for you to use, right? So I plug in what I know. The scale factor goes in here, and it happens to be a fraction, right? The new height, I don't know, right? It's unknown to me, but I do know the original is 12 centimeters. And voila, you're done. It's just calculating it now, right? Cross multiplying, dividing. 12 times 62 divided by 100. .44 centimeters. Height of similar can. There we go. That's how you do it. So this is the key. Remember, now that we're in scale factor, you kind of always want to go back here. I use this formula here as well, except for this was the scale. I without converting, I just kept the units separately, but it still works. All right, let's keep going. You might wonder sometimes, why are there blanks? Because sometimes I just put more than what I need, or I can come back and review the concept with you. Once we've done other stuff, it's like, hey, let's come back and do the extras, right? So let's skip it for now. Let's go to page 18. So now we're going to talk about scale factors involving 2D and 3D objects. Very important. So if you ever needed to be awake, this is the time to do it. Okay. So far we explored how scale factors affect the dimensions of an object, right? Let's put a little arrow, right? Dimensions would be length, width, height, radius, diameter. It's basically 1D, right? One dimensional. So or one dimensional. So when we talk dimensions, we're talking about the measurements that make up that shape, right? So we kind of had everything in centimeters, yards. There is no squared yards, square feet. None of that happened so far. Now we're going to start talking about that. How does enlarging or reducing an object affect the area, surface area, or volume? Okay. Let's explore. Consider the following rectangular prisms. Assume that the original has been enlarged by a scale factor of 2. So there's your original, there's your new. We are assuming that to go from here to there, right, we used a scale factor of 2, or if you want it as a percentage, right, you multiply that by, so 200% increase. Okay. So I think this is a pretty safe assumption to make, that the 5 here would be a 10 here, right? The 2 centimeter width would be 4 centimeters on the enlarged version, and the 3 would become 6. Okay. So there's your bigger box. Every dimension has been affected by a factor of 2, right? I think I'll just leave it at that. Don't make it too busy. Determine the dimensions, length, width, and height of the new prism. We did that already. Check. There it is. Determine the surface area of each prism. Okay, so we're going to find the surface area of this and the surface area of that. So let's go ahead and do that. If we take the original surface, that goes SA of original. We would go 2 times length times width plus 2 times length times height plus 2 times width times height. And now I'm having a flashback on that mistake I made last Friday, right? Forgetting to multiply by 2, so let's not forget that. Right, so this is surface area of this box right here. That's how you would find it. Okay. Surface area of original, therefore, turns 2. This is 2 times 5 is 10, times 2 is 20. 2 times 5 is 10, times 3 is 30. 2 times 2 is 4, times 3 is 12. So our surface area there is 62 squared centimeters. And I'm going to do the other one right next to it. Let's hope we have enough room there. The surface area of the new one, right, would be 2 times length times width plus 2 times length times height plus 2 times width times height. Surface area of the new. That'd be 2 times 10 is 20, times 4 is 80. 20 times 6 is 120. 8 times 6 is 48. And you get, you're not going to get double. You already know that it's not going to be double the original, right? It's not going to be 2 times 62, which is 124, right? It's not going to be it. This is going to be 80 and 120 is 200 and 48 is 248. What happened there, right? It's not twice as big. Everything like here, we just multiply everything by 2, no problem. That we could wrap our heads around, but if we find the individual surface areas, it's definitely not the case. So let's see how many times larger it is. So we're going to go surface area of the new divided by surface area of original. Okay, what happens when we divide those two? We're going to go 248 squared centimeters over 62 squared centimeters. I'm going to highlight in a bit, but for right now, just copy this. So when you divide them, the units cancel out nicely. And 248 divided by 62, some of you do mental math already because you're good at it. But if you divide them, it's 4 times. So if you wanted to fit this area into the new created, it would fit in there 4 times. If you were to fold these boxes open, lay them out on the ground, the small one would fit in there 4 times. Right? So this is 4, which is 2 to the power of 2. This right here is our scale factor, right? We used a scale factor of 2 to create the new one. So the area has not been affected by a factor of 2, but of 2 squared. Right? So here are some formulas that you need to make sure you have. If you're going to compare the surface areas, you need to make sure you take k squared. So we'll do this. Surface area of new over surface area of the original. That is one version of this formula. But we can't forget about diagram and actual. So I'll just rewrite this in terms of surface area of the diagram over surface area of actual. You should have these on your study sheet. Everything else I did was just to demonstrate that fact. And I think I have a little bit of room for some notes. Your writing is probably smaller than mine. I'm pretty, I use up a lot of space. Even though the dimensions were affected by 2, these surface areas are affected by 2 squared, which is 4. I hope that fits in your... What about the volumes? Volume is a little easier, thank goodness. If we look at the volume of the original, that would just be length times width times height, right? 5 times 2 times 3. So the volume of the original is 5 times 2 is 10, times 3 is 30. 30, and I would expect you to know that your units would be cubed, right? Because it's centimeter times centimeter times centimeter, like centimeters literally multiplied 3 times. Volume of the new one that we created would be, just look up at the numbers, right? 10 times 4 times 6. Okay. So volume of the new shape, that's 6 times 4 is 24 times 10 is 240. You can definitely see that the volume is not just affected by a factor of 2, right? This should have been 60 technically if it's just this times 2, right? But you can clearly tell it's not the case. Right? If the scale, if we're talking areas and we have squared units, we figured out that the scale factor will be affected by a factor of to the power of 2. Volume has cube units. I think you can probably imagine where this is going to go. If we were to say, hey, the volume of the new, if we divided it by the volume of the original, we would have 240 cubic centimeters divided by 30 cubic centimeters. Those cancel out just nicely. You end up with 240 divided by 30. How many times is the 30 going to 240, you might ask? 8, right? 8 times. How else can you write 8? 2 to the power of 3, right? 2 to the power of 3, there it is. And so K shows up still, right? But when we're talking volume, it will be to the power of 3. Okay, so here are my formulas for that one. K cubed, right? If we were to compare the volumes, that's what you get. If we're going to compare the volumes, it's K to the power of 3. I used to only give one version of the formula, and then students would have a hard time determining which one is the new and which one is the original when we're talking maps, blueprints, stuff like that. So I just give you 2 variations, but really we're doing this exact same thing. So these have to find their way to your study sheet. So there are really 3 different versions. There's K, when it's just dimensions that are linear. Then there's, if you're comparing areas, we need to make sure K is squared. If we're comparing volumes, we need to make sure K is cubed, okay? So we're going to kind of do the exact same thing that we've done already, but now we're going to deal with volumes and surface areas. So I invite you to go to the next page when you're done copying. That'll be page 19. And we're going to keep these formulas in mind, okay? Using the scale factor to determine 2D and 3D values, right? An ice cream shop is making a smaller cone for smaller children. Use the diagram to answer the following. Determine the scale factor used to create the smaller one, right? So the wording kind of gives it away. You're creating a new one, which is the smaller one, which is the replica. So this is, when it's replica, we can just say new as well. So you need to be creative here. If this is the original, for us, this means this is the new one we're creating, which is also called a replica. It's the same thing. Okay. So we're going to figure out the scale factor, no problem. Scale factor, I know that it's supposed to look as a fraction and no units have to be involved. And these are linear, correct? Linear dimensions, there's no squared units, it's just a diameter. So I will go new over original. That's it. So the new one is 1.77 inches, and the original has 2.5 inches. Okay, we cancel out the units. You see how there are decimals here? I would like you to get rid of that, so I will multiply both numerator and denominator by 100. You have to multiply both by the same. I choose to go 100 because there are two decimals up here. That would be 177 over 250. This is an acceptable scale factor right there. But I'm going to take it a step further and do the other formats just in case the question asks me to do it. Right, comma 0.708, and if you multiply that by 100, right, 70.8%. Just be comfortable stating it in the other formats, but this is the one I'm going to stick with. I don't want to round. In this case, it's a finite that doesn't keep going, so it wouldn't really matter which one you pick, but this is the one I'm going to choose to stay with. Listen carefully. Once you have a scale factor, guys, it doesn't change. You've determined how much they differ, right? How much has been changed in terms of their dimensions. So now we can use this for everything else. Determine the amount of waffle dough required to make the original cone. So you're asked to find the surface area. Surface area is at we're thinking 2D, right? So watch this, guys. We have both surface areas here, right? Under these cones, we have these ones. Maybe let's highlight. I'm going to stick with surface areas here. Right? They're basically unknown about how much dough, right? The dough that makes this. We don't know the surface area of the original, but we know how much dough is required for the new one. So here we go. Because it's two-dimensional, right? Can you please make sure you start off right? It's k squared now would be surface area of the new divided by surface area of the original. Bang, you got it. This is a good start. And now we're going to take our scale factor, which we found up here. Okay, so we're going to take that one. And unfortunately, a common error is students just drop the square. Right? You just told me that you're supposed to square that one, so you have to do the same here. We have a calculator, don't be scared, right? Just use it as is. The surface area of the new one has 10.15 squared inches, whereas the surface area of the original is unknown to us. And this is where you need to add an extra step to your work. I would like you to do this separately. So watch this, right? You're going to take 177, square it. Yes, it's a big number, but you just square it and write it down. 31,329, and take 250, square that one, 62,500. No big deal, right? That gets rid of the square outside the bracket, right? Boom. On the other side, nothing happens, right? You just write down exactly the way it is. And I'm going to call that X now. It's just easier. Notice, right? The only unit that shows up here is squared inches, which means that your answer will be in squared inches. Okay? So, to find X, we'll just go cross multiply like this, and then divide by what's left over. So 10.15 times 62,500. So yes, the numbers get bigger, but you get to use a calculator for everything. Okay, so you don't have to be scared of it. So 1015 times 62,500 divided by 31,329. That's 20.25 squared inches. I could now ask you, hey, what is it in squared centimeters? But I won't do that to you, right? But this is it. Right? Dough required to make the original cone. Determine the amount of ice cream the smaller cone can hold. And that should give it away the amount of ice cream something can hold or you can fit into something. We're talking volume, right? If it's not like this, look at the units that are provided to you, right? If you look at volume, it's in cube units anyways, right? I'm going to compare the volume here. I never highlighted surface area earlier, right? So I'm going to use the same color as I used there. And this is, you should immediately think 3D, which you should immediately think of k cubed. Can we do that? I'm just getting creative here. You should immediately think k squared up here. You should have. Down here, hey, it's 3D, so my whatever happens, my scale factor is cubed. The volumes are related by k cubed, not just k, not just k squared, k cubed. Okay. So here we go. K cubed is volume of the new over volume of the original. That's your starting point. My scale factor hasn't changed, right, guys? You're with me, right? You're with me? It's 177 over 250. And don't forget the cube. It's going to get really, these numbers are going to get huge here. And what do I not know here? So you got to make sure you do put them in the right place. I don't know the volume of the new one here. That one is unknown to me. So volume of new stays, and the volume of the original is 24.54 cubic inches. And yes, now you're going to have to do the dreadful 177. For powers, guys, look up here 1 second. Underneath clear, that hat takes it to the power of whatever you want, right? So 177 to the power of 3 is 55,45233. And 250 to the power of 3 is, make sure you get the right amount of zeros down, right? And on the other side, I'm just going to call this X, and this is 2454 cubic inches. So again, your answer will be in cubic inches in this case. X is equal to, you cross multiply this way, watch, right? You're going to go up multiplying, and then you divide going down. So it's 2454 times and I'll just give you the answer. That would be 9.06 cubic inches. Amount of ice cream the smaller cone can hold. And yeah, I think I've hopefully you understood what needed to happen there. I'm going to ask you to go to page 22. I'm going to get you to do a bit of work here. You're basically going to apply the same concept that we've just learned to these two questions, okay? So I want you to try both of these. Notice that they give you the scale, but it's already unitless, right? It's very easy to get your scale factor from that one. So apply what you've just learned, look at your notes if you have to, and then solve both of these. At least attempt them, right? For a couple minutes, and then I'll be back with a bit more for you. Take it back here for a bit. Way to go. The attempting part, I think, is there. So remember, when you're talking scale and you're given some kind of dimension, it could be right linear, like a squared unit or a cubic unit, you should be thinking it's either this one or this one or this one, right? Like one of these three, I'm going to use one of those formulas and plug in what you know and figure out the rest. In this case, it's cubed, right? So I'm going to use this one. Right? That tells me that I have to use that formula. Okay. If this is a scale, right, then I know that my scale factor is 1/15. I don't even have to convert to anything. It's already unitless, so we're good to go here. So let's jump on. K cubed, because of that cube there. Okay, it's volume of, so now I have to figure out, is this diagram, am I better off using diagram and actual? And because of the blueprint, this is what we call a diagram. So that means that we are going to be relating the measurements of a diagram with the measurements of the actual object that is being considered here. So this is your starting point. Plug in what you know. That should be 1/15 cubed. Volume of your diagram, let's see. If the capacity of the blueprint is this, right? This is the diagram. This right here is the volume of the diagram. Right there. Okay, so that goes up here. So that's 588.25 centimeters cubed over, we can call this x, right? And now you're starting. Now it's just a matter of filling in and solving it, right? So this would be 1/3,375 is equal to 588.25 centimeters cubed over x. Right? So you cross multiply and divide there. Divided by 1, which is irrelevant, and x will be 1985343.75 centimeters cubed. Now this is a big container. It's a really big container, so it probably makes sense to turn this into cubic meters. It could, very likely, but I'm going to just leave it like that for now. And that's my answer. Okay. Same with this one here. The amount of sheet metal required to build the actual container, right, is this. So sheet metal, right, is kind of like what you use to make those walls, right, of the actual container. So this is actually telling me that it's the surface area of the actual is provided here. Determine the amount of sheet metal required to build a container on the blueprint, right? Surface area of blueprint or diagram is unknown to me. Right? And watch out, once the scale factor has been determined, it stays the same, right? Like this doesn't change. Scale factor is still the same. It's ABC. I could have a bunch of questions. Once it's determined, it stays the same. So we'll go K squared, the surface area of diagram, over surface area of actual. And then I just plug in 1 over 15 squared. I'm given the actual surface area in squared meters. So this is my unknown here. So it's 1 over 225, right? You square both of them. That's x over 139.05. Make sure you show your work. Don't be too lazy to include the extra steps, okay? So that's 139.05 times 1 divided by 225. You can't see that, can you? Divided by 225, and so that gives you 0.618 squared meters. Convert, you can add this, convert to squared centimeters. If I asked you to do that, we take this 0.618 squared meters, and we know that 1 meter has 100 centimeters. We can't just do that, remember? We can't just cancel. What do we need to do to this ratio? We need to square it, and I think I gave you the actual ratio, right? But that'd be 0.618 square meters is equal to, right, this many square centimeters over a squared meter, and that's when you can cancel it out. And so basically the decimal will shift four places, right? There you have it. This is a complete aside. Just so you know, remember this step right here. It's in accordance to what we're doing here as well, guys. We can't just deal with square meters and keep everything else linear. We need to also turn this into squared units and then cancel out. I will right now, before I will do one more example, and I know I'm overloading you a little bit. I apologize for that, but I will write down the homework right down here. It's page 509, questions 4 to 8 in the textbook. And the wording is a little different, but I want you to get through that, okay? Let's go back a little bit. Notice that so far the scale factor was provided. But what if it's not? Right? So let's go back to page 20. Watch the title, scale factor from 3D values. It'd be the same as two-dimensional as well. Okay. And here's where I'm going to highlight something. We're making two cans, right? One can hold 322.57, or sorry, requires this much aluminum to produce. We don't know the surface area for this one. We also don't know the height of this new can, right? But watch what we know about both of them. We know their volumes. We know both volumes, right? And there's a bit of a problem. I just wanted this to be a real scenario. I'll tell you this. 1 ml is the exact same as 1 cubic centimeter. Did you know that? 1 ml is 1 cubic centimeter? Okay. I remember the bottles we used to buy, the 2 liter bottles would have it in centimeters cubed as well, the volume, if you bought a bottle of Coke. But anyways, so really we can say that this is 355 cubic centimeters and this is 500 cubic centimeters. Let's rewrite that because that's what we want to work with. Okay. It says determine the scale factor, right? What is K? That's what they're asking for. We know both volumes. You notice that? I highlighted it, right? So let's figure this out. We're working with volume, so we have to use this one. K cubed is equal to, what should we use here? What kind of wording should we use in this case? Diagram actual? Not really, right? We're making a copy or we're making a similar can. So this would be what? Original. And this would be the new. Okay. And it does say Coca-Cola has made a new, larger pop can. There we go. Lots of hints if you read. So we can't just use new and original. We have to use volume of new divided by volume of original. This one is very important. This is where you actually find the scale factor, because this is unknown. So you got to make sure you keep that cube there. We take the volume of the new, which is right here, 500 centimeters cubed. And we take the volume of the original, which is 355 centimeters cubed. Perfect. They cancel out, which should happen. That should be happening. And watch this. To get K all on its own, what do you need to do to the other side? Not square root, cube root. Cube root. Remember doing that in IPR? You had to do that. You had to break down the number, right? And find perfect cubes or perfect squares, right? What is he talking about? I forgot all about it. Anyways, don't worry about it. Cube root. Make sure you put that 3 there. And K is equal to, and this is where I need to introduce a new way of finding cube roots. It's kind of weird that they don't have a cube root button on this calculator. I don't know, I don't like that. But here we go, guys. I'm going to do it this way. I'm going to go 500 divided by 355, like that. Okay, so I'm going to divide these. And then I take the cube root of that. So you got to go math, press the math button, and you see cube root right there. The fourth option, go arrow down or press 4, whatever you like. And then I'm going to go up, copy, paste, right? Paste that into the root, hit enter, and there's your, and we technically only need to state our final answer to 2 decimals, right? I can multiply that by 100 and say that it's 112.09% as well. Does that make sense what I just did there? I had to cube root. Otherwise, you would have, if you just divided them, that was actually K to the power of 3. Watch, 1.12 times 1.12 times 1.12 get to that 1.40, which is what I started with when I just divided the 2, right? So you got to watch out there. So once you have the scale factor, this is staying the same, guys. Doesn't change. Okay? Doesn't change. Now you know. Can I ask you, how much larger is the new can compared to the original? The original is 100%. 12.09% bigger. Would that make sense? Right? Because you started with 100. This one is 112.09. What am I doing? Can't see that there, can you? You're the second group with this booklet, but I'm still making some tweaks to it. Right? So this is 100%. This can is 112%, so it's 12.09% larger. Okay, new can is 12.09% larger. I'm going to stop there. I want you to try B and C. Maybe if you still want to work a little bit longer, I'll give you the answer. Put this in brackets. This is on top of your homework. I want you to try these two as well on top of the homework, right? What did I say? 509, 4 to 8, right? So I'm going to write this down again so you have no excuses. 4 to 8 textbook. That's all for